Hey guys, welcome to our new day 9 content. So tomorrow we will be doing probability problems. We'll be practicing them together, checking in, making sure we all understand the big ideas. The first thing I want to go over with you guys in preparation for tomorrow is just how to do basic probability ideas. So probability is the study of chance. The probability that an event will occur can be expressed as a ratio of favorable outcomes to possible outcomes. Favorable to possible, all that means is just you're looking at how many possible ways could what you want happen out of how many total possible ways there are. So like flipping a coin, there are two total outcomes, right? Heads or tails. The favorable is what you want to happen. If I want heads, there's one way to get heads. So it's 1 out of 2. That's all that means, just what you want to happen out of the total what could happen. And you can write probabilities as 0 to 1, which is kind of like 0%, all the way to 100% is another way to think through that. When talking about probability in this chapter, we will be talking about theoretical probability, not experimental probability. So theoretical probability is just what the math says should happen. Experimental might not always be exact. So, theoretical might say that flipping a coin, you always get heads and tails 50% of the time. But theoretical probability, you might get heads a little bit more than 50% of the time. As experiments are, not perfect. The other thing to think about with experimental versus theoretical is that as you do more and more experiments, right, as you flip a coin more and more times, it will get closer and closer to 50%, which is the theoretical. Okay, so here are some examples. What is the probability of flipping a heads with a fair coin? We kind of just talked about that. It's a half or 50%. So you can write it either way, fraction, percentage, doesn't really matter. A positive integer less than 100 is selected at random. What is the probability that the integer is odd? So a positive integer smaller than 100, that's 1 to 99. And think back to some of our counting ideas. We are starting on an odd number and we are ending on an odd number. So when I think about the fact that about half of those should be odd, right? 99 divided by 2 comes out to 49.5. That means that about half of them should be 49.5, but we know that there's going to be more odd. So that means that there's going to be 50 odd compared to 49 even, right? It's going to trend a little bit more towards the odd. And if we want the probability that we pick an odd integer out of all of them, that would be 50 out of 99. Okay, always double check that you can't simplify your fraction anymore. 50 is divisible by 5 and 10s. I'm not seeing 5 go into 99. I'm not seeing 10. 99 is 9 and 11. And 9 and 11 don't go into 50. Okay. Why don't you try out number 3 just to see how you're doing with just the straightforward basic probability concept. I'm going to pause it and work through it. Unpause the video when you're ready to check. Hey guys, so here's the answer for number 3. It is 5 out of 36. I'm going to leave it as a fraction for my probability there. Now, this probability is 5 out of 36 because there are 5 total ways to get a 6. And I've listed them out here. Notice in this case, I am assuming that there is an order to my rolling of the dice. I'm assuming that 4 then 2 is different from 2 then 4. And it's kind of hard to know that you're supposed to assume that. So if you did it where that was only one way and 1 5 versus 5 1 was also 1, that's okay. You had logical thinking in that you were thinking that it was just a pair and that the pair was the same thing. So sometimes it's a little hard if they don't spell that out specifically. But that was what the problem was assuming, to do it this way. And then the reason why there are 36 total is if we think about our tree diagram. Your first roll, there are 6 total ways you could roll it, followed by your second roll, which is another 6. So for each of these 6 branches, there's going to be 6 more coming out. So 6 times 6 is 36. And that's coming from your fundamental counting principle. Remember, ways the first event can happen, ways the second event can happen, gets you your total. So that's just like the basics of probability. Probability gets a little bit more complex, and as you're writing this in your notebooks, I don't expect you to write everything down. You can just put a couple of bullet points of the big ideas, and I'll try and highlight the big ideas to help you guys make it a little easier. So while most probability problems you will encounter can be solved using counting methods from our previous chapter 2, or previous topic. Many will be easier to solve, by calculating the probability of multiple events, or compound. Compound events are basically just one event followed by another. So if you want to make a little note in your notebook, compound events, one event followed by another, right? And it could be 2 events, it could be 3, 4, and so on. And the key idea here with compound events is that there are 2 cases. There are 2 different types. One is called independent, and one is called dependent. And what they mean is independent is if the result of the first has no effect on the second. And dependent is where the first event does affect the outcome of the second. So I would put something of these 2 definitions in your notebook, right? You can put it word for word. You can put it in your own words. An example would be independent events are flipping a coin twice, right? Whatever you get the first flip doesn't affect your second flip at all. A dependent event would be that you have a bag of candy, let's say, and you take out one, but don't put it back, then take another. And so basically what this is getting at is that in your big bag of candy, let's say you have, a bunch of blue candies and some green candies, right? Right now, your chances of getting a blue or a green is the same 50-50. Let's say I take out a green and I don't put it back. Now, you're more likely to pick a blue than to pick a green because I have not put the candy back into the pile. Putting it back is something called replacing it. So put back, another way to say that is replace. And this will come up in a moment, so keep that in the back of your mind. If the probability of an event occurring is PA, probability of A, and the probability of a second event occurring is probability B, then the probability you have one than the other is just where you multiply them. And I think this is, useful to read through. It's useful to see. I think you don't want to get muddled too much in some of the equations. You want to really just think about the problems as we go through and think about them logically. If 2 events are mutually exclusive, meaning that they cannot both happen. For example, the probability of rolling a 7 or an 11 with a pair of standard dice, we can calculate the sum of the probabilities where you add them. So what this is meaning is that if I want to know the probability of picking a lollipop or a Snickers from my candy bag. Let's say I have 6 lollipops and 7 Snickers, and there's 25 candies, right? You would do 6 out of 25 plus 7 out of 25, right? And you would add those together to see what are your chances of picking either, because you don't really care about which candy you're picking. You just want one or the other. And it specifically says that they can't both happen just because sometimes when there's overlap, these problems get a little bit more complicated, right? But you can't have a lollipop that is Snickers flavored. That doesn't exist. So this stuff I wouldn't worry too much about. This stuff I think you'll see kind of come up logically in the problems. Like the candy example I gave you makes total sense to you, but seeing it this way might not make as much sense. Okay, so you can write it down in your notebook. You don't have to write down everything. Many probability problems involve blind selection of objects. If objects are selected with replacement, remember that means you're putting the object back. So this is another word to make sure you write down, and that's where you put the object back. The events are treated as independent of each other. However, if you don't replace the objects, one event can affect the other, right? So remember up top we didn't replace because it says we don't put it back, we don't replace it. Whereas an independent event, you always have to replace it back, and then one choice won't affect the other. And we'll see this come up as we look at some examples. So here are some examples where we can really see what the word replacement means, and I think this is really the best way to understand the term, is to just do a couple examples. So 4 green blocks and 3 red blocks are placed in a bag, and you pick them at random. And you pick one, then the other. So maybe I'll put one at a time. Okay. What is the probability of picking 2 red blocks without replacement, where we are not putting back? So the first red block, there are 3 of them, out of your total, which is 4 plus 3 or 7. So that's the chances I pick a red block the first time. The second time, I'm not putting it back, so there's only 2 total red blocks, and there's only 6 overall blocks to choose from. So remember, this is called a compound event, because you have first thing, then second thing happening. And that's just kind of the big idea of compound, is multiplying probabilities. This is the same thing as like if I flip a coin once, twice, 3 times, right? It's a half times a half times a half. You can also think of it that way because it's following a tree branch, right? If I was to fill in this whole tree branch, it would be 2 times 2 times 2, which is 8 total possible options. And there's only one way that I'm always getting heads each time. So it's 1 out of 8 total paths. So remember, it's really coming from your counting principle ideas of why we can multiply them like that. And then I get 6 out of 42, which you might have seen that you could simplify up here a little bit, right? 2 6 is the same thing as a third. This is going to simplify it to a 7th. So if you saw the simplifying at the beginning, you can also simplify at the beginning and cancel some stuff out. This compares to number 2. What is the probability of picking a green block and then a red with replacing? You are putting it back. So your green blocks, there are 4 out of 7. If I do put it back, notice here the difference is that the total remains, right? And then red block, there are a total of 3 red blocks. Notice that this one you're just picking the total because you haven't picked any red blocks yet, right? The total was changing up here because you weren't putting them back and you had already picked one of the red blocks. So just kind of keep in mind some of the small details. And then you've got 12 out of 49, and that should not simplify. So not the biggest chances of selecting in that order. Okay, this next one is going to be a little bit more complicated. What is the probability of selecting 3 blocks of the same color with replacement? Now, they don't specify what color. So let's figure out the probability of red, 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 as well as the probability of green, green, green. And we'll do them separately and then decide what we want to do. So probability of red, 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 if we look back at the beginning, we are told that there are 3 red blocks out of 7. So 3 out of 7, 2 out of 6, 1 out of 5. Right? Keeping in mind that your numbers are going down 1 each time because you have a new total and a new total of red blocks. And the probability of getting the first green is 4 out of 7, and then it's going to go down 1 each time, right? 3 total greens, now 6 total blocks because I'm not putting them back, and then 2 followed by 5. So I've simplified the fractions just to make it a little bit faster, and then because I don't care which option it is, all green or all red, you can add them together, which gets you to 5 out of 35 and simplifies to 1/7. So this is a good example of that OR idea that we were talking about on the previous page, adding the two probabilities together. Okay, so we will continue a little bit in the next video because I'm running out of the time that I can make a free video with. See you then!